Welcome to this walkthrough of LeetCode problem number 1488, Avoid Flood in the City. In this session, we'll explore the problem requirements, discuss various approaches, and dive into the most efficient solution. Stick around to strengthen your problem-solving skills and gain insights into tackling similar challenges. Imagine a city struck by a severe storm, where multiple lakes are at risk of flooding. Each lake is uniquely identified by an integer, and you are given an array called rains. In this array, if rains I is greater than 0, it means that it rains on the lake with ID rains I on the ith day. On the other hand, if rains I equals 0, this represents a day where you can take action to dry any one lake of your choice. The challenge is to prevent any lake from flooding. A lake floods if it rains on it again while it is already full, that is, it has rained on that lake previously, and it hasn't been dried since. Your task is to return an array called result of the same length as rains. When it rains on a given day, the corresponding element in result must be -1. If it's a day where drying is possible, the value in result can be the ID of the lake you chose to dry, or it can be arbitrary if no drying is needed. However, if it's impossible to prevent a flood, you should return an empty array. Let's take a look at the first example. Here, rains is 1, 2, 3, 4. On day 1, it rains on lake 1, so result 0 is -1. On day 2, it rains on lake 2, so result 1 is -1. Similarly, on days 3 and 4, it rains on lakes 3 and 4 respectively, and the corresponding values in result are also -1. Since no lake has rained on more than once, and no drying is needed, the result for this example is -1, -1, -1, -1. Now, let's consider a slightly more complex scenario. In the second example, rains is 1, 2, 0, 1, 2. On day 1, it rains on lake 1, so result 0 is -1. Day 2 sees rain on lake 2, so result 1 is also -1. On day 3, there's a 0, giving you the opportunity to dry a lake. You choose to dry lake 2, so result 2 is 2. On day 4, it rains on lake 1 again, and result 3 is -1. Finally, on day 5, it rains on lake 2 again, and result 4 is -1. This keeps all the lakes from flooding, and the result is -1, -1, 2, -1, -1. Now consider the third example. The input rains is 1, 2, 0, 0, 2, 1. On day 1, it rains on lake 1, so result 0 equals -1. On day 2, it rains on lake 2, making result 1 equals -1. On day 3, you have the opportunity to dry a lake, and you choose to dry lake 1. As a result, result 2 equals 1. On day 4, you dry lake 2, so result 3 equals 2. On day 5, it rains on lake 2 again, and result 4 equals -1. Finally, on day 6, it rains on lake 1 again, so result 5 equals -1. This sequence of drying and raining ensures no lake floods, and the result is -1, -1, 1, 2, -1, -1. For this problem, certain constraints and edge cases must be considered. The length of the rains array is between 1 and 100,000, and the values in rains range from 0 to 1 billion. Since each lake is represented by a positive integer, and 0 represents a day where drying is possible, the algorithm must handle these inputs efficiently. For edge cases, consider when the array contains only zeros. In this situation, no rain occurs, so the output can be any valid array of the same length. Conversely, if there are no zeros, meaning there are no drying opportunities, the output must simply be -1 for each day. Finally, when the input size is very large, the solution must remain efficient in terms of both time and space, ensuring it can handle up to 100,000 days without performance issues. To solve this problem, we considered several approaches, starting with the brute force method. The intuition behind this approach is straightforward. For each day, if it rains on a lake that is already full, we check for the earliest available dry day before the flood occurs. If no such dry day exists, flooding becomes unavoidable. To implement this, we maintain a record of which lakes are full, and whenever we encounter a conflict meaning rain on an already full lake, we iterate through the dry days to find one that can resolve the issue. However, this method has a major drawback. It involves nested iterations, as we check each dry day for conflicts. This results in a time complexity of O(n) squared in the worst case, making it impractical for large inputs. While simple to implement, the inefficiency of this approach makes it unsuitable when scalability is important. Now, to address this limitation, we consider an optimized approach leveraging binary search combined with a data structure like a tree set in Java or a sorted list in Python. Here, the idea is to avoid iterating through all dry days by using binary search to efficiently locate the earliest available dry day. In this approach, we maintain two key data structures: a map to track the last day each lake was filled and a sorted set for the indices of dry days. When it rains on a lake that's already full, we use binary search to quickly find the next dry day. If such a day exists, we dry the lake and remove that day from the set. If no dry day is available, flooding occurs. This approach reduces the time complexity to O(n) log n, as binary search operations are much faster than linear iterations. While more efficient, it does require additional implementation complexity to handle the sorted set or binary search logic effectively. Another optimization we explored uses a greedy approach in conjunction with a hash map. The key idea here is to prioritize drying the lake that is at the greatest risk of causing flooding next, rather than relying on binary search. This eliminates the need for maintaining a sorted set. For implementation, we track the last day each lake was filled using a full map and maintain a list of dry days. When it rains, we check whether the lake is already full. If it is, we traverse the list of dry days to find the earliest one that can prevent flooding, then use the dry day and remove it from the list. On the other hand, if the current day is a dry day, we simply add it to the list for potential future use. While this approach is intuitive and simpler to implement than the binary search method, it has a downside. In the worst case, traversing the list of dry days can still degrade to O(n) squared time complexity, especially when dry days are sparse or poorly distributed. Despite this, the greedy logic often proves faster in the average case, making it a reasonable alternative when simplicity is prioritized over guaranteed efficiency. Ultimately, the chosen strategy for this problem is the optimized approach that combines binary search with a set data structure. A critical insight here is that we only need to dry lakes that are at immediate risk of causing flooding. This allows us to avoid unnecessary operations, focusing solely on resolving conflicts as efficiently as possible. Binary search is the cornerstone of this approach, as it enables us to quickly locate the next available dry day without iterating through all options. Using a tree set or a sorted list for the dry days is what makes this efficiency possible. This method achieves a worst-case time complexity of O(n) log n, which is ideal for handling large inputs. The key advantage lies in its balance between performance and implementation complexity. While the brute force method is too slow for large datasets and the greedy approach can fail to perform consistently in edge cases, the binary search-based solution provides scalability and reliability. This makes it the optimal choice for solving the problem effectively while maintaining a manageable level of code complexity. In this problem, we are tasked with managing water levels in a sequence of lakes over several days. On some days, it rains on a specific lake, filling it with water. If a lake that is already full receives more rain, it will flood. On other days, we have the option to dry one lake, meaning we can empty its water to prevent potential flooding. Our goal is to determine a schedule for using these dry days to avoid flooding or to conclude that it's impossible to prevent flooding. The input consists of an array called rains, where each element corresponds to a day. If the value is greater than 0, it indicates that it rained on the specified lake that day. If the value is 0, it is a dry day. The challenge lies in using these dry days strategically to empty the right lakes at the right time to avoid flooding. The output of the algorithm should either be a valid drying schedule or an indication that flooding cannot be avoided. To solve this problem, we need to use several key data structures. First, we use a set called full_lakes to keep track of which lakes are currently full of water. This helps us quickly check if a lake is at risk of flooding. Next, we use a list called dry_days to store the indices of days that are available for drying. These dry days are a limited resource, so we need to use them wisely. Finally, we use a dictionary called last_rain to map each lake to the last day it rained on that lake. This helps us determine when a lake was last filled, which is crucial for deciding which lake to prioritize for drying. At the beginning of the algorithm, we initialize these structures. We also create an output array called result, where each element corresponds to a day. Initially, this array is filled with -1, and we will update it as we determine the drying schedule. Now, we process each day in the rains array. If it rains on a particular day, we check whether the lake receiving rain is already full. If the lake is full, we need to find a dry day to empty it before it floods. We look for the earliest dry day that comes after the last time it rained on this lake. If no such dry day exists, flooding is unavoidable, and we return an empty schedule. If we find a valid dry day, we use it to dry the lake, mark the lake as no longer full, and update the result array to reflect this action. If it is a rainy day and the lake is not full, we simply mark the lake as full and record the day in the last_rain dictionary. On the other hand, if it's a dry day, we add the day's index to the dry_days list and tentatively set the result for that day to 1, which we might revise later depending on how the dry day is used. Once we finish processing all the days in the rains array, we handle any remaining unused dry days. These dry days can be assigned to dry arbitrary lakes, as they won't impact flooding at this point. We update the result array to reflect these assignments. Finally, we check whether flooding occurred during the process. If no flooding occurred, we return the result array as the drying schedule. However, if flooding was unavoidable, we return an empty array to indicate that no valid schedule exists. The key insight here is to use dry days strategically. By maintaining the last_rain dictionary, we can prioritize drying lakes that are most at risk of flooding. Additionally, we make the dry day search efficient by keeping the dry_days list sorted so we can quickly find the earliest valid dry day for a given lake. This greedy approach ensures that dry days are used in the most effective way possible to prevent flooding. The data structures we use play a crucial role in the efficiency of the algorithm. The full_lake set allows us to quickly check, in constant time, whether a lake is full and at risk of flooding. The dry_days list is used to store unused dry days, and if implemented as a sorted list or with a binary search mechanism, it allows us to efficiently find the earliest valid dry day for a lake in logarithmic time. Finally, the last_rain dictionary maps each lake to the last day it rained on that lake, enabling us to track when a lake was last filled. This is especially important for determining which lake to prioritize for drying. Together, these data structures ensure that the algorithm remains efficient while handling the complex requirements of the problem. The algorithm is efficient both in terms of time and space complexity. The main loop processes each day in the rains array, which takes n time. For each rainy day, searching for the earliest dry day using binary search takes log n. Since we perform this search at most once for each rainy day, the overall time complexity is n log n. The space complexity is linear, n, due to the storage required for the full_lake set, the dry_days list, and the last_rain dictionary. It's also important to consider edge cases. If there are no dry days in the input, flooding is unavoidable if any lake is filled more than once. If there are excess dry days, they can be assigned arbitrarily since they don't affect the outcome. Additionally, when multiple lakes are full, the algorithm ensures that each dry day is used optimally to prevent flooding as early as possible. Let's walk through an example to understand how the algorithm works. Suppose the input is rains equals 1, 2, 0, 1, 2. On day 0, it rains on lake 1, so we mark lake 1 as full. On day 1, it rains on lake 2, and we mark lake 2 as full. On day 2, it's a dry day, so we add index 2 to the dry_days list. On day 3, it rains on lake 1 again, which is already full. We use the dry day at index 2 to empty lake 1, preventing flooding. On day 4, it rains on lake 2, which is already full, but no dry days remain to empty it. As a result, flooding is unavoidable, and the algorithm returns an empty array. This example highlights the importance of using dry days strategically to prevent flooding whenever possible. Here, we start by importing the sortedList class from the sortedContainers module, which will help us efficiently manage and search through the list of available dry days. Inside the solution class, the avoidFlood method is defined to handle the problem. We initialize a variable n to store the length of the input list rains, and create a result list filled with -1, representing the default value for days when it rains. Additionally, we use a dictionary called full_lakes to keep track of the most recent day each lake was filled, and a sorted list named dry_days to maintain an ordered list of days available for drying lakes. The loop iterates through each day and the corresponding lake in the rains list. If the lake number is greater than 0, it means it's raining on that day. We then check if the lake is already full by looking it up in the full_lakes dictionary. If the lake is full, we use the bisect_left method on dry_days to find the earliest available dry day after the last rainy day for this lake. If no such day exists, meaning there are no available dry days to prevent flooding, we return an empty list since it's impossible to avoid a flood. Otherwise, we pop the earliest dry day from dry_days and update the result list to mark that day is used to dry the lake. Finally, we update full_lakes with the current day as the most recent day this lake was filled. If it's a dry day, indicated by a lake value of 0, we simply add the day to the dry_days list and temporarily set the result for that day to 1 as a placeholder. After completing the iteration through all days in the rains list, the result list is returned as the output. This list represents the sequence of actions taken to manage the lakes, where -1 indicates it rained on that day, and any positive number specifies which lake was dried on a dry day. This ensures that we avoid flooding in the city while adhering to the constraints of the problem. Here, we begin by importing the necessary Java utilities and defining our solution class. Within it, we declare the avoidFlood method, which takes an integer array called rains as input. This array represents the sequence of weather events. Positive numbers indicate rain filling a specific lake, while zeros represent dry days. First, we initialize some variables. The length of the rains array is stored in n, and we create an integer array called result, which will hold the output. Initially, we fill this array with -1 to indicate rainy days by default. Next, we set up two key data structures, a hash map named full_lakes to track the last day each lake was filled, and a treeset called drydays to store the indices of dry days in sorted order. Now, we iterate over each day in the rains array using a for loop. If the current day indicates rain for a specific lake, we first check if that lake is already full by examining if it exists in the full_lakes hash map. If it does, we need to find the earliest dry day to prevent flooding. Using the ceiling method of the treeset, we locate the smallest dry day index that is greater than the last rainy day for this lake. If no such dry day exists, it means flooding is unavoidable, and we return an empty array as the solution. Otherwise, we use the dry day to empty the lake, updating the result array and removing the used dry day from the tree set. Finally, we update the hash map to indicate the current day as the last rainy day for this lake. If the current day in the rains array is not a rainy day, we handle it as a dry day. In this case, we simply add the day's index to the dry days tree set, marking it as a potential day to resolve any future flooding issues. We also initialize the result array at this index with a default value of 1. This serves as a placeholder, and it will be updated later if this dry day is actually used to empty a lake. Once the loop completes, we return the result array, which now contains a sequence of actions that either specify the lake to dry on a dry day or remain -1 for rainy days. This ensures that all potential floods are avoided while respecting the constraints of the problem. In this first example, we are given the array rains equals 1, 2, 3, 4. Each number represents the lake that receives rain on that day. Since there are no zeros, or dry days, we will focus on marking each lake as full and ensuring no lake overflows. We start with an initial setup, where the result array is initialized to -1, -1, -1, -1, representing no dry days. The full_lakes map is empty, as no lakes are full yet, and the dry_days list, which would store the indices of dry days, is also empty. On day 0, Lake 1 receives rain. Since Lake 1 is not in the full_lakes map, we mark it as full and associated with day 0. As no action is needed, the result for this day remains -1. Similarly, on day 1, Lake 2 receives rain. Again, it's not in full_lakes, so we mark it as full and associated with day 1. The result for day 1 is also -1. Now, on day 2, Lake 3 receives rain. Since it's not already full, we add it to the full_lakes map and associate it with day 2. The result for this day remains -1 because no further action is required. On day 3, Lake 4 receives rain. Like the previous days, this lake is not yet in the full_lakes map, so we mark it as full and associated with day 3. The result for day 3 is -1. Since all the lakes in this example receive rain only once, and there are no dry days, we successfully avoid any flooding. The final output is simply -1, -1, -1, -1, indicating that no lakes needed drying and no flooding occurred. In the second example, rains equals 1, 2, 0, 1, 2, we encounter a scenario where a dry day is available, and some lakes receive rain more than once. Here, we must use the dry day effectively to prevent flooding. Once again, we start with an initial setup. The result array is initialized to -1, -1, -1, -1, -1, the full_lakes map is empty, and the dry_days list is empty. On day 0, Lake 1 receives rain. Since it's not yet full, we mark it as full and associated with day 0. The result remains -1. On day 1, Lake 2 receives rain. Similarly, it's not in full_lakes, so we mark it as full and associated with day 1. The result for day 1 is also -1. On day 2, we encounter our first dry day, denoted by 0. We add this dry day to the dry_days list, making it sorted list 2. As no lake needs drying immediately, we leave a placeholder value of 1 in the result array for now. On day 3, Lake 1 receives rain again. However, Lake 1 is already full, so we must use the dry day at index 2 to empty it. We remove this dry day from dry_days, making it an empty list again, and update the result array to indicate that Lake 1 was dried on day 2. The full_lakes map is updated to reflect that Lake 1 is now full again, with the most recent rain occurring on day 3. The result for day 3 remains -1, as no additional action is needed. On day 4, Lake 2 receives rain again. This time, Lake 2 is already full, but no dry days are available. Consequently, flooding occurs, and the output is an empty array, indicating that it was impossible to avoid flooding. In the third example, rains equals 1, 0, 2, 0, 1, 2, we have 2 dry days available, which allows us to manage the lakes more efficiently. As before, we begin with the initial setup. Result is initialized to -1, -1, -1, -1, -1, -1, full_lakes is empty, and dry_days is an empty sorted list. On day 0, Lake 1 receives rain. Since it's not full, we mark it as full and associated with day 0. The result for this day remains -1. On day 1, we encounter a dry day. We add it to the dry_days list, making it sorted list 1. As no lake needs drying yet, we place a placeholder value of 1 in the result array. On day 2, Lake 2 receives rain. It's not in the full_lakes map, so we mark it as full and associated with day 2. The result remains -1. On day 3, we encounter another dry day. We add it to the dry_days list, which now becomes sorted list 1, 3. Again, no immediate action is needed, so we update the result array with a placeholder value of 1. On day 4, Lake 1 receives rain again, but it is already full. We use the earliest available dry day at index 1 to empty Lake 1. We remove this dry day from dry_days, leaving it as sorted list 3. The result array is updated to reflect that Lake 1 was dried on day 1, and we mark Lake 1 as full again with the most recent rain on day 4. The result for day 4 remains -1, as no further action is needed. Finally, on day 5, Lake 2 receives rain again. As Lake 2 is already full, we use the next available dry day at index 3 to empty it. We remove this dry day from dry_days, leaving it empty. The result array is updated to indicate that Lake 2 was dried on day 3, and we mark Lake 2 as full again with the most recent rain on day 5. The result for day 5 remains -1. With no flooding and all lakes managed properly, the final output is -1, 1, -1, 2, -1, -1. This output reflects that we successfully used the dry days to prevent any overflows, efficiently managing the lakes. To analyze the time complexity of our solution, we start with the first step, which is iterating through the rains array. Here, we traverse the entire array once, contributing O(n) to the time complexity, where n is the length of the array. On rainy days, when a lake receives rain, we need to check if it is already full. This involves a dictionary lookup using full underscore lakes. Dictionary operations like lookup and update are O1, so this part is efficient. However, if the lake is full, we must find the earliest available dry day after the last rain for that lake. To do this, we use the bisect underscore left method on the dry underscore days sorted list, which takes O log m, where m is the current number of dry days stored in the list. Once we identify the appropriate dry day, we remove it from the list using pop, which is another O log m operation. While m, the number of dry days, is bounded by n, this means that each rainy day operation involving dry day management is O log n. Combined, these steps contribute to the overall complexity of handling rainy days. Now, for dry days, when the lake value is 0, we simply add the day index to the dry underscore days sorted list. This insertion operation also takes O log m, and since m is at most n, we can represent this as O log n per dry day. Putting it all together, the dominant factor in our time complexity arises from the rainy day operations, which involve O log n work for each day. As the rains array has n elements and each day involves operations that are either O1 or O log n, the overall time complexity of the solution becomes O n log n. Moving on to space complexity, the first component to consider is the result array, which stores the output. This array has a fixed size of n, contributing O n to the space complexity. Next, we consider the full underscore lakes dictionary, which keeps track of the last rainy day for each lake. In the worst-case scenario, every lake in the rains array is unique, meaning the dictionary could store up to k entries, where k is the number of distinct lakes. Since k is bounded by n, this contributes O n space in the worst case. Additionally, the dry underscore days sorted list holds the indices of dry days. In the extreme case where all days are dry days, this structure would also require O n space. When we sum up these components, the result array, the full underscore lakes dictionary, and the dry underscore days sorted list, the total space complexity amounts to O n plus O n plus O n, which simplifies to O n. Finally, we can evaluate the best, average, and worst case scenarios. In the best case, no lake fills twice without an available dry day, so operations on each day are O1, yielding a total time complexity of O n. In average cases, some lakes require dry days, leading to O log n operations per rainy day, making the total complexity O n log n. The worst case occurs when every rainy day triggers a conflict, requiring dry day resolution for each, resulting in O n log n complexity as well. To understand how this solution compares to a naive approach, consider the brute force method. In the naive approach, for every rainy day, we would scan all previous dry days to find a valid dry day to empty a lake. This would result in a time complexity of O n squared. In the worst case, as for each rainy day, we might need to check up to O n dry days. Our optimized solution, however, uses a sorted list, which allows us to efficiently find and remove the earliest available dry day in O log n time. This improvement reduces the overall complexity from O n squared to O n log n. To mathematically verify the big O complexity, note that for n iterations of the loop, and each iteration involving O log n operations for sorted list insertions, deletions, and lookups, the total number of operations is bounded by n asterisk O log n, confirming a time complexity of O n log n. On the space side, the storage requirements of the result, full underscore lakes, and dry underscore day structures are all proportional to n, leading to a space complexity of O n. Common mistakes in solving this problem often arise from not handling dry days efficiently. For example, some solutions assign dry days arbitrarily, without considering which lakes are most likely to flood in the future. This approach can lead to unnecessary flooding, as dry days aren't used strategically. Another frequent error is using brute force to select dry days. Iterating through all available dry days each time a lake needs attention significantly increases the time complexity, making the solution impractical for large input sizes. Additionally, overlooking edge cases, such as consecutive rainy days with no dry days in between, can lead to runtime errors or incorrect results. These scenarios are critical to address, as they often reveal whether your solution can handle unavoidable floods appropriately. Now, another common mistake is failing to use an efficient data structure to track which lakes are full. Without a structured approach, such as using sets or dictionaries, updates and lookups become slow and cumbersome, which can hinder performance. It's also important to validate input constraints. Assuming all inputs are valid can lead to undefined behavior, especially if negative values or unexpected input lengths occur. From an interview perspective, this problem often tests your ability to recognize patterns, such as its similarity to greedy or interval scheduling problems. A successful strategy involves prioritizing dry days for the most urgent needs. Interviewers may guide you toward efficient solutions by hinting at data structures like heaps or ordered maps. When explaining your approach, focus on how you track full lakes, allocate dry days, and handle edge cases. This clarity demonstrates both your solution design and your understanding of the problem. This problem also shares concepts with other challenges on LeetCode, such as non-overlapping intervals, minimum number of arrows to burst balloons, queue reconstruction by height, and insert interval. Exploring these related problems can provide additional insights and techniques. As for alternative approaches, one option is a greedy method that utilizes a priority queue. Here, you use a min-heap to track which lake needs to be dried next, prioritizing the lake with the nearest flooding risk. While this approach is highly efficient with a time complexity of O(n) log n, it requires careful implementation to maintain heap order. Another alternative is a set-based simulation, where full lakes are tracked using a set. When a lake is about to flood, the nearest dry day is used to address it. This method is simpler to implement than a heap-based solution but may become less efficient for larger inputs. An additional alternative approach is the sliding window technique, which can be helpful in specific variations of this problem. This method involves using a fixed size window to allocate dry days within a restricted range. The idea here is to match dry days to immediate flooding risks within that constrained window. However, this approach is only applicable if the problem specifies a fixed use-by range for dry days. While the sliding window method can simplify implementation in such scenarios, its applicability is limited, making it less versatile than other solutions like heaps or sets. Understanding these trade-offs is crucial when choosing the right strategy for different variations of the problem. Great job making it to the end. In this problem, we explored how to efficiently handle flooding scenarios using a combination of hash maps and heaps. Remember, the key takeaway here is the importance of combining data structures to solve complex problems. Thanks for watching, and don't forget to like and subscribe for more coding tutorials. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!